don't care about the damage. We care about people.
Why did they make these cars so crushable? What's the idea of having crushable cars? The answer to that question is safety, right? So when you have a crushable car, somehow it's going to make you safer. Except this kind of safety is real expensive because this car is totaled at 40 miles per hour. This car is totaled at 40 miles per hour. 40 miles per hour is a fast parking lot speed. It's an average texting speed. You simply didn't see the building coming. So how does making a car crushable make you feel safer? How does that work out?
It like embraces it.
Say it again.
It embraces the impact.
Keep yourself 5 points. Furthermore, why not just make the outside indestructible, put the safety on the inside? Right. So this is an overview of the lecture. All right. So what kills you, what maims you, what breaks your bones is acceleration in essence. All right. So the cars are built to reduce the acceleration as much as possible during impact. That's what they do. So, for example, if you're exposed to 75 G's of acceleration, up to a few minutes, it can potentially kill you. So the question is how.
3, 2.
All right. So here's the video that you guys had seen before.
This video will read
In the lecture link. This guy is exposed to 7 G's of acceleration. He's a medical doctor. He's inside a centrifuge. And centrifuge is actually spinning at a constant speed as this guy is exposed to 7 G's. Eventually what's happening is he's feeling relaxed. And then he starts to black out. And he's out at this point. The eyes are open, and then they will stop the experiment right now. So the question is, why did he pass out? The answer to that question is because he was accelerating. So what happened within his body that caused him to pass out? That's what we're investigating. So he was exposed to 7 G's, and at 7 G's, this guy passed out. Now imagine that you're driving your car in the forward direction. So what happens to your body? You feel a push in the opposite direction of the acceleration, right? All right, into the backward direction. You put the brakes on, the car is slowing down, now the acceleration is in the forward direction. So the only thing you need to know is whenever the vehicle is accelerating, you will experience a force in the opposite direction of the acceleration of the vehicle. So that's what happens. So the unstrapped objects inside will move in the opposite direction of the acceleration of the vehicle. So those of you guys who are religious, watch Jesus accelerate. Notice that he's having a hard time keeping up with this cross. Acceleration can be a religious experience. What's the difference between a Ford Tempo and a BMW? It's the price tag, guys. All right, so BMW is extremely expensive because it can go from 0 to 60 miles per hour within less than 4 seconds. Ford Tempo, it's an extremely cheap car. They discontinued the model like 20 years ago. Down a hill from 0 to 60, maybe about 2 minutes. All right. So imagine that I'm driving my souped out Ford Tempo in the forward direction at 7 G's. So what's going to happen to my body? I'll feel a push in the opposite direction of the motion, right? What happens to the blood in my body? Well, it's going to start to move in the opposite direction of the acceleration of my body as well. So what happens to the blood in my head, in my brain? The blood is going to start to pull towards the back of my head, towards the back of my brain. Eventually, obviously, the blood is going to drain away from the frontal lobes towards the back of my head. And so lack of blood, lack of oxygen, eventually I'll pass out. Okay, so that's what happened to that medical doctor. Unstrapped objects will always move. They will always move in the opposite direction of the acceleration of the person, the object, or the car, or the vehicle that you're in. Except we got a slight problem. The problem is the guy inside the centrifuge, he wasn't speeding up. He wasn't slowing down. All right. He was moving at a constant speed while experiencing about 7 G's of acceleration. So how do we induce acceleration at a constant speed? All right, so what do we know so far? We know that the speeding up is acceleration, so it's slowing down. Okay, so in this case, you're not speeding up, you're not slowing down, but you're changing direction. So it's possible that changing the direction is also acceleration. Let's test it. Right? So you got a pendulum. When the car accelerates in the forward direction, the pendulum backwards in the opposite direction of the acceleration. You put the brakes on. All right, so car is slowing down. The pendulum moves forward. So what that means is it moves forward when the acceleration is backward in the opposite direction of motion. And note that in circular motion, the pendulum still moves, and it moves away from the center of the circle. And you know that the pendulum is always going to move in the opposite direction of acceleration. So which means that the acceleration has to be directed inward in circular motion. All right, now this explains everything. Now imagine that you're the pilot sitting up with your back against the wall. So the wall is right here, right? So the acceleration is directed towards the center, which means that the blood is going to drain away from the center towards the back of your head. So that's what it means. So that's the reason why the guy passed out. Okay, so out of that, we end up getting a definition for acceleration. So acceleration means speeding up. Let's just focus on this one. Slowing down and changing direction. So how fast do you speed up? how fast you slow down, how fast you change your direction, is how fast your velocity changes in time. So how fast the velocity changes in time becomes the formal definition. It becomes the formal definition of acceleration. So the acceleration is how fast the velocity changes in time, in essence. All right, so mathematically, it looks like this. So here's your initial velocity, here's your final velocity. So your velocity is increasing in the forward direction within this time period. All right, so the velocity is going to be expressed in terms of meters per second. Time is in terms of seconds. So the acceleration is going to be expressed in terms of meters per second squared. So that's what we end up getting out of it. For safety reasons, we will express it in terms of G. G feels like your own body. All right, so G feels like your own body. So what does it feel like to be exposed to 7 Gs? 7 times your own body. 10 Gs, 10 times your own body. All right, so that's in this formula. What's changing is the velocity on the right-hand side, but your velocity is changing from this moment in time to that moment in time. All right, so T represents the time between two measurements. These are your measured velocities. These are your instantaneous velocities, which means that your instantaneous velocity is the one that's changing in time. All right, so changing measured velocity in time is going to be acceleration. For safety reasons, we'll express it in terms of G's. The proper unit is meters per second squared. All right, so speeding up is acceleration. If the acceleration points in the direction of motion, it's positive, indicates that the object is speeding up. If the acceleration is pointing in the opposite direction of motion, which means that it's negative acceleration, which means that the object is slowing down.
1950s,
All right, so we focused on John Stapp experiment.
years before the Pinto or Corvair.
This guy was strapped onto a rocket sled, and then he was accelerated up to 632 miles per hour. And then he was brought to a stop within 1.4 seconds. And the extent of the damage was his retina got 2 times. All right, so 632 miles per hour. So he was going at 632 miles per hour. He was brought to a stop, final speed is 0 within 1.4 seconds. So what was his acceleration? All right, so I'm doing the conversions to the metric units. In terms of G's, final speed is going to be 0. Final mathematical expression looks like that, like the numbers in it. And it's going to give you about 20 G's, right? That's what we end up getting, roughly about 20 G's. That's what we got. So this guy was exposed to 20 G's for a week, and he did survive. He volunteered for this experiment, and he did survive. He was in charge of the experiment, so he decided to do it after conducting some animal experiments. So he figured that it was survival. So 20 G's is survival. So we end up getting a finding, which becomes crucial. This guy conducts experiments. He realized that you can easily survive between 20 to 25 G's. About 25 G's, you start to break down. Right, so what do we know? We know that 75 G's up to a few minutes, survivable. 20 to 25 G's up to a few seconds is also survivable. So higher the G's, the lower the duration is usually.
The impact, that's only about 2 seconds. Newspapers have talked luridly of speeds of 120 miles an hour, but looking at the damage tells a very different story. It suggests an impact with the pillar of about 60 miles an hour. And we know that the car came to rest about 15 feet from the pillar, spinning out, and that means about 10 miles an hour exit speed from the pillar.
All right, so this is the Princess Diana accident. 4 people in the car, 3 dead, 1 survived. Survivor survived barely. He was in a coma for a month, maybe 2 months. All right, so what went wrong? In all appearance,
After the impact, exit.
Looking at the damage on this car, a lot of people assume that people died because this accident wasn't survivable. When you run the numbers though, all of a sudden you realize that the car's acceleration was 22 G's. And you know you can survive between 28 to 25 G's easily, up to a few seconds. Car's acceleration was 22 G's for 1/10 of a second. John Stapp survived something like this for a duration which is 14 times longer than this. So that means that this is survivable. You've got 4 people in the car, 3 dead, 1 survived, and 1 survived barely. All right, so change in velocity. Estimated change in velocity is 50 miles per hour. Estimated impact time is going to be 1/10 of a second for the calculation reasons. And we got the impact time from the crumple zone. So what's the purpose of the crumple zone? To increase the impact time. That's it. The purpose of the crumple zone is to increase the impact time. So what happens when you increase the impact time? Acceleration goes down. All right, so with the impact time increased to 1/10 of a second because the engine compartment crumples, and all of a sudden this thing becomes survivable. All right, now your acceleration is up.
Strangely, Princess Diana, sitting where I am in the right rear, had the best chance of survival because the impact was concentrated on the left front of the car, and as it hit the pillar, it also rotated and span out, so she went partly past the pillar and didn't have quite the same crash forces applied to her as happened to the people sitting on the left. If she'd been wearing a seatbelt, she'd have had a fair chance of surviving.
She wasn't wearing a seatbelt, dead. Fiance sitting next to her was not wearing a seatbelt, dead. Driver was not wearing a seatbelt, dead. The only person who was wearing a seatbelt was seated in front of her, the bodyguard. He survived, but he survived barely. All right, so wearing a seatbelt, why does it make a difference? It makes a big difference because this is super slow motion. Entire impact, this is a 40-mile-per-hour car collision, car crash testing. Entire impact is going to last a tenth of a second.
Even this extreme accident.
And this is super slow motion as the car is still crumpling.
But unbelted, she was thrown forward to strike the back of the front passenger seat.
Then it goes forward, makes contact with the back of the front seat, and then gets thrown back.
The door pill.
This impact, the impact time, is much shorter than the car's impact time. That's what the problem is. All right, so while the car's impact time is roughly about 10th of a second, this is less than 10th of a second. This is probably 10 times shorter of an impact time than the car's impact time. All right, so not wearing a seatbelt, you're going to end up hitting the first thing in front of you. It may feel pushy, just don't get misled by it. It's not going to give you a large enough impact time for the most part. In the worst case scenario, you're going to hit a dashboard, steering. It's going to bend a little bit. And the best that they could do for you is going to be 100th of a second. All right, so if you're not wearing a seatbelt, your impact time is going to be shorter than the car's impact time. Shorter than impact time is the larger the acceleration is. All right, so her acceleration was around 200 Gs. The car's acceleration was around 20 Gs.
If she'd been wearing a seatbelt, she'd have had a fair chance. And then,
on top of that, notice that there's also a change in direction. So this acceleration is going to be larger than 200 Gs in essence. So with this seatbelt, your impact time is the same as the cars. At reasonable speeds at 40 to 50 or 60 miles per hour, the cars are designed to be survivable. The impact is survivable. All right, so it's going to be around 20 Gs. Without the seatbelt, your impact time is going to be much lower.
6,000 miles away, Swedish engineers came up with the same answer. The three-point seatbelt was introduced by Volvo in 1959. Volvo patented the device, but allowed everyone else to use it free of charge.
The whole purpose of the seatbelt is so that you're attached to the car so that your impact time is the same as the cars. That's it. All right, that's a simple solution to a deadly problem. Be attached to the car. The cars are designed to crumple in order to increase the impact time so that the acceleration is survivable at reasonable speeds. So let's
in an area underneath the driver so that
what do we know? 7 to 12 Gs, up to a few minutes, 20 to 25 for a few seconds. So the question is, what is the maximum acceleration that you could be exposed to and still be able to potentially survive?
Researchers estimate that when Fittipaldi crashed,
1996,
he felt
this accident
nearly
revealed something.
100 Gs.
So when they pulled out the black box data, they noticed that this driver was exposed to a little bit over 100 Gs for a fraction of a second.
That means
so the maximum acceleration was about 100 Gs.
For a fraction of a second, Fittipaldi.
He fractured his neck in 2 places. He did recover, he survived. So all of a sudden, the car companies go, oh, so it's 100 Gs is survivable. And then ever since then, they've been looking at black box data from accident scenes. And when somebody survives, they update the numbers. So far, under extreme circumstances with extreme constraints, you may be able to survive up to 140 Gs.
They have the weight of a dump.
So that's where the numbers are. So 20 to 25 Gs is survivable up to a few seconds. And you can possibly survive between 100 to 140 Gs under extreme constraints. Right? So which means that you have to have the head and shoulder gear so your head is stabilized, or else your head is going to become 100 times heavier, so that can actually break your neck. So you have to have the proper constraints for this to work. All right, so why not build to make the cars indestructible and put the safety on the inside, like the airbags or whatever. All right, so when you make the car indestructible, your impact time is going to be relatively short. Right? Your impact time is going to be almost non-existent. Let's put it this way. So your impact time becomes infinitely small. So it's like 0. So your impact time starts to tend towards 0. That's the way we say it in mathematics. So whatever the change in velocity is, the same change in velocity. So any number divided by 0 is going to be infinite. So which means that the acceleration of the vehicle would be infinitely large. All right, so car companies would not build indestructible cars because they would generate a non-existent impact time. With that, the acceleration would be infinitely large. That's it. All right, so my question is, make the car indestructible and put the safety on the inside, like the airbags or whatever. All right, so why not do it that way? Safety on the inside. The airbag increases the impact time. Soft landing, right? Increases the impact time. So it's going to increase the impact time up to a second. All right, so with the airbag, it's Princess Diana's car accident. With the airbag, it would have been 2 Gs for the people on the inside. So the acceleration would have been 2 Gs. But were they wearing their seatbelts, they would have been exposed to about 20 Gs. That would have been survivable. So the problem was not a single person was wearing a seatbelt outside of the bodyguard, so those people did not survive. The bodyguard ended up surviving, barely. So what happened, Princess Diana ended up going forward, hit the back of the front seat, broke the back of the front seat. So the bodyguard lunged forward, smashed his face against the dashboard, and he immediately passed out. The guy had no recollection of the accident. He still doesn't. All right, so accident by accident, the side impact collisions tend to be the deadliest. All right, so the reason is, once again, because of acceleration. We got the crumple zones built front as well as the back of the vehicles. So the engine compartment is a crash zone, and the luggage compartment is a crash zone as well. So people get your impact time from your crumple zones, in essence. So it'll give you about 10th of a second at 40 to 50, possibly 60 miles per hour. From the side, the cars are not built to crumple that much for obvious reasons, because you got passengers inside, people inside their seatbelt, they got no places to go. They got no place to go. So you don't want to crush people to death. If they have to go, the acceleration is the best way to go. You don't want anyone to feel any sort of pain, obviously. All right. All right, so there are a couple of ways to avoid side impact collisions. Forget this, avoiding the side impact collisions. A couple of ways to avoid deadly side impact collisions, not necessarily the side impact collisions. At all costs, avoid direct impact to your body. All right, so this tends to be deadly. All right. Not the car necessarily, so this is the thing to avoid. If the car takes a hit, it'll go into a spin motion relative to its center mass. In most cases, this is survivable. If the backside of the car takes a hit, once again, the car is going to spin. So once again, in most cases, this is survivable. Spin acceleration tends to be survivable than direct impact. If you have side impact collision airbags, certainly going to help. I mean, if you're getting hit, if you don't have it, more than likely you cannot survive something like that. So with or without side impact airbags, try to avoid, it makes no difference, just try to avoid direct impact to your body and try not to hit someone directly.
It's a disaster waiting to explode, and then it does.
All right, so you see an accident like that,
This is a very
is it survivable or not? I always check to see where the dents are if I'm driving by. All right, the dent is here. I know it's a side impact collision. This is survivable. So what happened? The car went in a spin. Driver didn't take a direct hit.
serious accident. The innocent victim survives.
Next thing I see the truck coming, wonder why he's going, it's my turn, basically. And next thing I know, someone's after me, I lose my glasses.
Now on its last leg, the mangled truck piles into a parked 18-wheeler. This trucker, realizing the danger, flees on foot. The cops quickly arrive on the scene and swarm the vehicle. The man's pulled out and arrested. Suspect in custody.
Yeah, he passed out briefly, so that's the extent of it. So what's acceleration? It's speeding up, slowing down, and changing direction. All right, so before you guys took physics, you're thinking, you know, speeding up is acceleration. So you get that far. Sometimes you realize that when you're slowing down, that's also acceleration. We say deceleration, it's the same as acceleration, it's negative acceleration. Proper unit is meters per second squared. G is the expression of acceleration in terms of one's own body weight. So 7 Gs feels like 7 times your own body weight. 10 Gs feels like 10 times your own body weight. I'm losing my voice. So unstrapped objects will move in the opposite direction of the acceleration of the vehicle. Speeding up is acceleration because your speed is changing. That's number one. Number two, if you're driving, unstrapped objects will move backwards. You'll also experience a push in the opposite direction of motion. Slowing down is acceleration because once again, your speed is changing. And once again, the unstrapped objects, if you're driving, will move forward and you will feel a push in the forward direction, in the opposite direction. In the opposite direction of the motion or acceleration of the car. Not the motion of the car, but the acceleration of the car. If you're moving at a constant speed while changing direction, because you're changing direction, you're still accelerating. Because number one, you will experience a push in the opposite direction of the acceleration of the vehicle if you're inside the vehicle. Or if you have unstrapped objects inside the vehicle, they will move away in the opposite direction of the acceleration of that vehicle. So the proper definition of acceleration is how fast you speed up, how fast you slow down, and how fast you change direction. So it's a combination of speed and direction. It can be expressed as a combination of speed and direction. So it can be expressed in terms of velocity. That's what it means. How fast the velocity changes in time is the proper definition. All right, so when you say how fast the velocity changes in time, it encompasses everything. It encompasses speeding up, slowing down, changing direction. So how fast you speed up, how fast you slow down, how fast you change direction. All right, so we know from the pilot training experiments that you can survive easily between 7 to 12 Gs up to a few minutes. So that's for a few minutes, 7 to 12 Gs. It's considered a survivable zone. You can survive more, but that's where usually the testing usually takes place. G-load testing usually takes place in the military. So from John's step experiment, we know for a fraction of a second, you can survive between 20 to 25 Gs. for a fraction of a second. From black box data, we know that you can survive between 100 to 140 Gs for a fraction of a second. Right? Purpose of crumple zones in cars is to generate an impact time. Right? So generate an impact time, generate a large enough impact time. So impact time goes up, the acceleration goes down. Acceleration is what kills you, what maims you. So the whole purpose of the crumple zone is to generate an impact time, large enough impact time, so that the acceleration is survivable. If the cars were made indestructible, you wouldn't have that impact time. So no impact time means nearly infinitely large acceleration. So that would not be survivable. All right, so the crumple zone is going to generate an impact time. If there's no crumple zone, there would not be a large enough impact time. So the acceleration would be extremely large, nearly infinitely large. All right, so now we're dealing with typical accelerations. All right, so typical acceleration at 40 miles per hour in crash testing is going to be about 20 Gs. Typical acceleration at 40 to 50 is going to be about 20 Gs by design. People are seat belted, their acceleration is going to be the same as the cars at crash testing at 40 miles per hour, so it's going to be about 20 Gs. If the person is not wearing a seat belt, typical acceleration is going to be about 200 Gs. It's going to be 10 times larger than the car's acceleration. So impact time is smaller, acceleration is larger. If there's an airbag, it's going to be about 2 Gs to 3 Gs at 40 miles per hour. Side impact collisions tend to be deadlier than the frontal impact collisions because of the lack of crumple zones. They're crumple zones, but they're not really designed to generate large enough impact. All right, so they're going to create a little bit of an impact time to usually deploy the airbags. All right, so they're there to deploy the airbags if there are airbags. How do you avoid a deadly side impact collision? Avoid a direct impact to your body, or try not to hit someone directly. All right, if you're about to cause a side impact collision, if you can avoid a direct impact in anybody's body in the car that you're about to hit, that's how you avoid deadly side impact collision.